Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide, and it's Semester 2, 2025. This is a revision seminar for Statistics and Numerical Methods. The last seminar for Statistics and Numerical Methods, because this course is being broken up into other courses in the future. So, well, I guess hello to everyone doing it this year, because everyone in the future, who knows? Yeah. Okay, I've had some requests and I will talk about some things. There's a good reason I'm doing this one instead of Nicholas, because this course has statistics in it and I'm the most confident with statistics in the Maths Learning Centre. So if you get me, then I'm happy for you. The other staff do know things, and at least between them they can figure things out. But if I'm there, wave me over. But I'm sure you're not the only ones who will want to do that. Yeah, okay. So I'm just going to let my subconscious work on the Taylor's theorem and do some stats first. And I was specifically asked to talk about ANOVA, so I will start there. So ANOVA is a very strange acronym for analysis of variance. So analysis of variance. Fun fact, it is the 100th anniversary of ANOVA this year. It was first published in 1925. And it was first used to study agriculture. There you go. Subsequently used for eugenics, but you know. And this is why nobody likes Fisher. Okay, so Fisher died here in Adelaide, actually. He's from England. He invented this there, and he died in Adelaide of tuberculosis, and his bones are in St. Peter's Cathedral. And he was a eugenicist, so suck it. Okay. So I'm just going to check what your notes say about ANOVA. Thank you very much for letting me borrow them. Why do they make it so complicated? Oh, for the... Really? It's just so ridiculous. Okay. So this may be a slightly different perspective from what your lecturer told you, but it helps me think about it, so I'm going to tell it to you. The purpose of most statistical procedures that you are taught is to decide whether things are related to each other. So most stats is about, that you've been taught, all right, most stats help decide if variables are related. That is a useful and important truth. Any statistics that is used to help decide the answer to a yes or no question will produce a p-value. That's what hypothesis tests are for. They are for deciding the answers to yes or no questions. So decide yes or no is a p-value. Just so you know, the other purposes of statistical procedures, there are 4. One is to answer the question of like what's happening, which means you generally draw a graph. Deciding the answer to yes or no question, that's what p-values are for. And trying to find what a number is, that's what confidence intervals are for, just so you know. And then trying to find not just whether things are related, but exactly how they're related. That's what regression is for. What ANOVA does, ANOVA is firmly in this category. Yep, thank you. Okay, before I forget, this is your revision seminar. Please, exactly as you did, tell me if I need to move the page, ask questions, tell me if I've made a mistake, all of those things. They're important. I will try to stop every 5 minutes or so, but if I forget, just ask me to stop. You can even ask, your question can even be, David, stop writing for a couple of minutes so that I can catch up. It's a perfectly legitimate question. Okay, so they are the main purposes of statistics. If you look through the statistics you've been told, anything that produces a p-value is designed to answer a yes or no question. That can be helpful when you're reading an exam question and the question gives an answer of yes or no, then you know that you're going to have to produce a p-value along the way. Or in this course, in an exam, read a p-value somewhere and interpret what it means. Traditionally in this course, the exam has been, here is some stuff that MATLAB produced, now interpret what it means. In general, that's how it runs. Okay, ANOVA fits in this category here, and depending on what kinds of variables are involved, that changes what statistical procedure you do. So whether those variables are categorical or, in this course they probably call them quantitative, but categorical and numerical, that makes a difference as to what kind of statistics you do. Because categories, you can only really do percentages, but numbers, you can do means. Right, so the purpose of ANOVA is to answer a question like this. So ANOVA answers questions like, if I move this whole thing down, that'll be easier. ANOVA answers questions like this. There's some categorical variable, which usually is different ways that things are treated, but it could be just features that they have. And you want to see whether that is related to some numerical outcome, some category and some number. And ANOVA is specifically designed for when this categorical variable has more than 2 categories. That is what ANOVA is for, to answer the yes or no question of whether that relationship is there. I know it says that the arrow goes this way, but statistics isn't capable of knowing which way the arrow goes. It just tells you whether there's a relationship or not. But most research will be attempting to prove that this is true, because if you design your experiment correctly, you'll know what causes what. So, yeah. I will say that your individual objects or people or whatever they are will all have to have different ones in different categories. So there'll be, in this category, will be a different group of people or objects or whatever or whatever it is you're studying. Different ones will have to go in different categories, as opposed to everyone being in every category and measured multiple times. That's different. So this is the picture I draw when I help people like medical students or whatever, or veterinary students decide what statistics to do. I draw the relationship that I'm interested in and pick boxes for categories and scales for numbers. And then when I look at this picture, I go, oh, that's ANOVA. Okay, so that's what ANOVA does, is designed to answer this question. And what it produces at the end is a p-value, because it's a test. It doesn't have the word test in its title, but it does produce a p-value. And all hypothesis tests produce a p-value via a test statistic. So the p-value is the goal, but the only way to know a p-value, because it's a probability, is to attach it to a particular number and know what's the probability of that number being something. So the goal is you'll get some data, there'll be a calculation, you'll get a test statistic, and then you'll get a p-value. And the test statistic in ANOVA is called F, for Fisher, because he invented it. Well known to be a smug bastard. Gossett, who invented the t-test, didn't name it after himself. So, yeah. Also, he published his work under a false name so everyone could use it, even though his research belonged to the Guinness Beer Company. So Gossett, follow Gossett, Stan Gossett, he was fabulous. Fisher was horrible. But he gave us ANOVA, so I guess it's not all bad. Okay, sorry. I say that in every seminar where ANOVA turns up because I think everyone should hate Fisher, really. I like to say that he refused to explain anything he thought was obvious, and the tradition in statistics teaching has continued to this day. Okay, so that's how it works, and just it'd be good to have an example in your mind. There are many examples you could have, but the example in my mind is actually this, which is I group groups of people a meal and measure their body temperature afterwards. Meals have no chili, chili powder or chili paste. And then my question is the kind of chili you have related to your body temperature? That's a classic ANOVA situation. Every individual person has a different kind of chili. So some people have chili, no chili, some people have chili powder, some people have chili paste. And we all measure the temperature for everybody. So the picture that goes here is chili. I'll put the title at the top. Which comes in 3 types, which is none, powder, none, powder and paste, and different people are in each of these categories for the situation I put them in, and I want to know whether that makes a difference to temperature, which is a perfectly good number. That's the story. That's my picture of the story, and that's why I know it's ANOVA. Without any data I can't do anything now, but at least I know that it's ANOVA. And it wouldn't matter how many different categories there were here, it would still be ANOVA. If there were 2 categories, I would do a t-test. Because that's the t-test is ANOVA, but for 2 categories. So note. Is the t-test. Technically the 2-sample t-test. Is that what they call it in this course? Or do they call it the unpaired t-test? 2-sample t-test. Do you know what my picture looks like if it's a matched pairs t-test? Everybody's in both boxes. So while we're at it, the way to decide between the 2-sample t-test and the matched pairs t-test is in the matched pairs t-test, every participant, be they a person or a petri dish or whatever they are, is in both situations. And the pair that we're talking about is the pair of measurements that go with each person or thing. And so in me, that's the way I do it. They're in both situations, whereas in this one, every person's only in one of those situations. Yeah. There you go, that's it. There is such a thing as it's not called paired because there's more than one. There is such a thing as an ANOVA where everybody's in all situations, but you weren't taught that. But it does exist. Most possibilities for how to draw this diagram exist somewhere. Yeah. So that's just a side note of how I make decisions of what stats goes with what. I need to pull this out a bit. Yeah. If you go to the Maths Learning Centre, there's actually a set of cards in one of the boxes in the cupboard that has a whole lot of stats tests and the picture that goes with them, if you're ever interested to look at it. So, all right, that's the vibe. That's what it's for. The question of how to use it is a whole different thing, and I will still talk about that too, but I hold on to what it's for so that it makes it easier for me to process what's happening. Okay. So, all hypothesis tests, as I said, produce a test statistic, and then I have to calculate a p-value, which is a probability. So I have to compare the test statistic I get with my data to all the test statistics that could possibly have been. So the way that you get your test statistic from your data, and you compare it to the test statistics that could have been, and that's what produces a p-value. All probabilities are always a comparison between something and all the things it could have been. That's what probability is. And the name for the test statistics that could have been is the distribution of the test statistic. So what this means, that's the distribution. And every test, so hypothesis test, the T, the ANOVA, the whatever ones you've done, they all have a distribution to go with them. And in our case, it's called the F distribution for ANOVA. In the T-test, it's called the T distribution. And in, I don't know, did you do proportion things? It's a Z. Did you do chi-squared? It's a chi-squared. They're usually named after the distribution. Or the distribution is named after the letter. That sometimes happens too. So ANOVA is the only one that doesn't mention the name of the distribution in the title. So in this case, it's the F distribution in our case. And you need to know just enough information to tell exactly which F distribution it has. So with the T distribution, you need one number to tell you which one it is, and it's called the degrees of freedom. With the F distribution, you need two numbers to tell you which one it is, and they are both called the degrees of freedom. And so it will be with this number and this number, degrees of freedom. For me, the degrees of freedom is like an address. It's the distribution finder, DF. And it's like, okay, so it's got this street number, this 7th Street and number 5, that's the house where I knock on the door and ask the F distribution what my probability is. Because in my head, all the distributions live in this city. So it's just an address for looking it up. And a modern computer has ways of looking up the probabilities to go with which one, but you have to tell it what the address is. Back in the day, we'd all have to use a table that was printed and go to the right page and then the right row to get the one you want. So that's how the address works. Okay, and the F distribution looks like this in general. And you're going to put your test statistic here, and this is all of the test statistics that could have been, and your p-value is going to be over here. And whatever that area is, that's the probability we're looking for. I'm jumping around in a whole lot of different orders because it's just what's occurring in my head. But I find it useful to have some of these things without knowing the details, to say, look, I know when I do ANOVA, the goal is to get a p-value and it will produce an f, and that f will produce a test statistic. That f will produce a p-value. When you do ANOVA, the computer will tell you what these degrees of freedom are, what the value of f is, and what the p-value is. And the reason it tells you all of that information, even though all you need to know is the test at the p-value, is so that you can be, or someone can be sure that it's working the way it should. Okay. The big question is, how do you get from your data to the test statistic? And in ANOVA, that's the most complicated one we have. And it is based on variances, which is why it's called analysis of variance. And a variance is the thing that you would get just before you do the square root when you calculate a standard deviation. In fact, the word variance was invented in order to talk about ANOVA, which is funny because it's an acronym for a word that hadn't been invented yet. So it's just, the history of statistics is full of that sort of ridiculousness. Okay, here we go. In my head, ANOVA works like this. These are my three possibilities for chili. No, powder, paste. And then this is my temperature. And I can draw a dot for every person to say what their temperature is. And so in the no chili, maybe their temperature's here, and maybe in the powder, their chili's here, their temperature's here, and in the paste, they're here. I know, I'm making up crap. And these are all the individual people and their measurements of temperature. When I look at this picture, it seems obvious to me that if you have powder or paste, your temperature is higher, but if in these, it's not that different. Maybe it's more variable with the paste than it is with the powder. Okay, that's what this graph says. And ANOVA is trying to create a p-value to confirm that thinking that you have. And the more mixed together two groups are, the less you'll believe that there's a relationship. That's the idea behind it. And so each of these groups, at the moment, this group doesn't mix together with the others very much, and so it's going to come out with a low p-value for my ANOVA. Because the lower that p-value is, the less I believe, the more I believe there's a relationship. Okay, we're back. The more I believe there's a relationship. So remember, the p-value is your level of belief in the fact that there's no relationship. It's all a proof by contradiction to say, if there's no relationship, my f would have been really low, but it's really high, and the p-value is really low. Like the higher f is, the lower p gets. That's basically how it works. Because this p-value is this area, the further out this gets, the lower that area becomes. And so the p-value is this cutoff, and if it's too low, then you're going, my level of belief in that null hypothesis is like 0.02. Nah, I don't believe it. That's the idea. Don't say it that way to a statistician. Just say the p-value is under 0.05 and therefore we reject the null hypothesis. But you can think of it as the level of belief in the null hypothesis. Okay, so the way ANOVA works is that you figure out the mean for each individual group. And then you say, if the group means are further apart from each other than the individuals within each group, then I think the group makes a difference to the result. Like which category you're in. So I can if there's no relationship, then these categories don't make a difference to the result. And it's all just one big group. So what I do is I compare... Stop, David. If I wanted to know, try to predict what someone's temperature would be, I know with this one I should probably take into account what kind of chili they were given first, according to this graph. And so if I wanted to know their temperature, I would kind of need to know what the average temperature is for people who had paste, and then add a bit of randomness up or down, and that should be approximately what their temperature is going to be. But if this didn't make a difference to the result, I should just figure out what the grand total mean is for everyone and add a bit of randomness because it doesn't really matter what group you're in. That's the idea. I imagine when I put them all in one big group, sorry, I'm overlapping the other one, and this is my grand mean here. I'm comparing how far everybody is from this grand mean to how far everybody is from their local mean. That's the idea. Actually, I'm comparing it to how far each of these local means is from the grand mean. Okay. And it's very like regression in that matter. In regression, you figure out how far everybody is from the line of best fit and compare that to how far everybody is from the mean. That's how regression works. So when you do the slope in regression, you've got, yeah, anyway, that's just a whole lot of stuff. Officially, ANOVA is a kind of regression because it does look very similar. It's just that there's only 3 spots instead of an entire line's worth of spots to be. That's the idea behind it. So I'm just going to look it up just to make sure I get it right. I'm looking, this is the note, so I'm looking for this table here. I'm skipping some of the this crap, and I can come back to that, but I just wanted to get the overall idea, because when you ask a computer to do an ANOVA, it will produce a table like this. Hopefully. Nope. Okay, so what it will be doing in the background is calculating these means and this mean, and for every individual in the data, it will figure out how far it is from the local mean, how far the local mean is from the overall mean, and also how far it is from the local mean. There's 3 different distances from the big group mean. There's 3 different distances you can calculate, and they are called bear with me. Oh, that's two-way ANOVA. I am too far ahead. Okay, so I'm just going to write this down. This is my group mean. This is the grand mean of the entire group. And this is me. And there are 3 distances involved. There is this distance, how far I am from my group mean. There is this distance, how far I am from the grand mean. And there is this distance, how far I am from the group mean. Those 3 things are calculated for every individual and added up, and squared first. You square them and then you add them up. And so you add up how far everyone is from their local group mean, and you square all those numbers and you add them up. And that sum of squares is called SSR. Nope. Wait. SSE. So the sum of the squares of all of these, this is SSE. Because it's called error, because the idea is that the best estimate I have for what your number is going to be when I try and predict it is your group mean. Because I don't know what the random bit's going to be. And so the error is how far you are from your group mean, because that's the bit that you're going to get wrong if you use the group mean to predict the answer. The sum of squares of this bit this is SST. It's the total sum of squares. It's how far everyone is from the grand mean. And that's the idea that if the groups doesn't make a difference, then the best estimate I have of everyone's score is going to be what the mean is for everybody. And this is SSR. That says sum of squares, by the way. I left all my text in the Maths Learning Centre. And in regression, a regression table will give you all three of these things. But I will say this distance between the group mean and the grand mean, you include it in the total once for every person. Not just once for each group, once for every person. That's really important, because otherwise the numbers won't add up correctly. Okay, and so in the table, it will say source group error total. The number in this spot is, well, the number in this spot is the SSE, definitely error in that spot. And the number in this spot is SST, because it's the total, and this one must be the other one. Right, so this is just here for interest, to make sure that you are all the numbers are adding up correctly. It should be true that this plus this equals this, because this plus this equals this. That should be true. That should be true. The next thing they have is the degrees of freedom. And the degrees of freedom is based on the situation in the story. So, the degrees of freedom is how many of the bits of information you can change without guaranteeing to change the mean. So I can change all but one of the values without guaranteeing to change the mean. If I change all the values, I'll guarantee to change the mean. And so this is n minus 1 here. The group one, well, that's based entirely on the group means. And so this will be the number of groups minus 1. I think they call it G. Oh, they've called it K, but what is? G for groups. And this is what's left. These two things should add up to each other. So this will be n minus g. So that this plus this adds up to this. So if I were asked to fill out one of these tables, it has been a classic exam question in the past to give you an ANOVA table with gaps in it and ask you to fill out the missing bits. And so they'll give you an ANOVA table with two of these, usually this one and this one, but usually that one and one of these, and ask you to fill out the other one, and you go, aha, well, I'll go to SST minus the other one. And this one they won't give you any because they'll have told you the story, and you'll know how many groups there are, and you'll know how many people there are in total, and you can fill out these numbers just from that. And then the next part of the table is this, and it is called the MSE, the MS, which is the mean squared error. And each one of these is that divided by that. So you go SSR divided by its degrees of freedom and SSE divided by its degrees of freedom. So you divide the total amount of variation, which is what this is, by how many different things can vary, and you get the mean square error. And then the final answer is your F statistic, and your F statistic is that divided by that. So it is this divided by this. So it is the MSR and the MSE. Yeah. So this thing's called MSR. This thing's MSE. Damn it, David. And F is MSR divided by MSE. Yay! That is how to do an F. Now, you won't be actually doing this part in your exam because that's based on the entire list of data. You can't do that in your exam. But theoretically, they could give you just 2 of these and the story, and you should be able to figure out what all the other ones are. But I haven't had anyone tell me that that's happened recently, so the most likely thing to happen is that they'll just give you the entire ANOVA table and ask you to interpret the results. But I just wanted to say, that's how they're built. Fisher was obviously a very clever man to have come up with this sort of thing. Like, what the hell? That's how it's done. And then there will also be a p-value over here. And that will be based on that graph I drew. Yep. So, and you would say something like, if you were in MATLAB and you wanted to know what the p-value was, you would have to type in a CDF command for the F distribution. I don't know if they teach you that, but you would have to do that. So all of the p-values are based on a CDF of some distribution. The t distributions from the t-CDF. It is CDF, right, how they do them? When you do calculations of probabilities, it's like PDF and CDF. In R, which is a computer program they use over in maths, it's P and Q. Yours is a little easier to remember. But you'd have to use a CDF command to figure out what the p-value was. Like 1 minus F CDF. Like, just so you know, I don't know if this is useful, but it's 1 minus F CDF, and you put the degrees of freedoms, and then you'll put the F statistic. And you put the degrees of freedoms from these 2 boxes here. And you put the top one first and the bottom one second. So this is the top and bottom. And they are literally called the top and bottom CDFs because they are the top and bottom of the fraction. So not CDFs, degrees of freedom. Okay, yay. So in general, the bigger the degrees of freedom are, there's 2 fractions divided by each other and everything affects everything else. So if this degrees of freedom got bigger with this one staying the same, then the F statistic would get lower, which would make the p-value higher. If you've got 20 groups, it's really hard to get a low p-value because there's just not enough information across all of them. The more groups you have, the more data you have to compensate for the degrees of freedom. Yeah. And that's how ANOVA works. But at the end, the conclusion is the same. You look at the F statistic and go, cool. Not the F statistic, the p-value, and go, cool, it's 0.02. I conclude that there is a significant relationship between Chile and whatever. It doesn't tell you which group is different to which group. It just tells you that at least one group is not the same as at least one other group. So the null hypothesis that goes with it, and here we go, it should be that the null hypothesis is just words and says there is no relationship between these variables. That should be what the null hypothesis is. It makes sense, goes with the story, but statisticians really love null hypotheses to mention parameters, and so you're going to have to write it to mention parameters. And so in this story, the null hypothesis would be, they write H0, right? Would be the mean for no chili is the mean for powder, which is the mean for paste. Something like that. You could use 1, 2, 3 if you wanted. You could use letters if you liked. It doesn't really matter as long as you know what they mean. And the null alternative hypothesis, do they use a little a? The alternative hypothesis is words. It is not all equal. There's only one L in equal. I mean, you should say the means are not all equal, but not all equal will be just good enough, usually. You shouldn't put this with not equal signs between them, because that's not the same thing. That would mean that none of them is equal to any of the others, but technically that's not the opposite of all of them being equal. The opposite of all of them being equal is that some of them aren't equal. So you could say some are not equal, that's another way of saying it. But traditionally it's not all equal. But in my mind it's there is no relationship or there is a relationship, but this is how you say it. Yeah, and then if you're going to mention parameters, you have to say where mu no is the true mean temperature with no chili, and then etc. You have to say what all of them are. So they always say you have to define your parameters. That moment where you say what the letters stand for, that is defining your parameters. And if there is usually at least a mark for it across the whole exam. There was one exam I said, look, if they only define their if they don't define their parameters ever in the exam, then you get no marks, and if they do define it at least once, you get 1 mark. But some people write their exam that there's a mark for it in every question where it's necessary. So just it's a good thing to do every time, just in case. Okay, that's ANOVA. It's at this point that you should ask some questions or tell me that you don't have any. Oh crap, I've thought of one, but you might have one. You know how I said ANOVA doesn't tell you which group is different to which group? Yeah. If you want to do that, you're going to have to do some extra work. And it is called multiple comparisons. What page was I up to? 4, I think. So, here's the thing. Officially, if you are now asking the question, which group is different to which group, you are now asking, so I'm just going to draw a little picture here. We originally had 3 categories, and we want to see whether this made a difference to that. But if now you want to know which group is different to which group, I'm just going to call them A, B, C, then you want to compare A and B and how that makes a difference to the result, and you want to compare A and C and how that makes a difference to the result, and you want to compare B and C and how that makes a difference to the result. They are all t-tests, because that's what you do when there's only 2 categories. So if you want to go further and say, if you're not happy with, oh yeah, it does make a difference, and you want to know which one makes more of a difference than which one, then you have to do a collection of t-tests. Every possible pair has to be compared, and this is called multiple comparisons. Which MATLAB can do for you, and it produces a big table that says which one compared to which one, and there's a p-value for each one. You know, A compared to B, there's a p-value for that, A compared to C, there's a p-value for that, A compared to D, there's a p-value for that, and it's done it all using this calculation, which is very fancy. Officially, you could do a t-test separately for each one, but it's very clever because you're borrowing the standard deviation from everybody, even the ones that are in Group C, when you're comparing Group A and Group B. Sweet. Yeah. This is called the Bonferroni method, where what they've actually done is they have adjusted the p-values. But I'm not sure if they've adjusted the p-values or if they've adjusted the cutoff. Give me a second. Doesn't say. I think I'm going to trust that MATLAB adjusted the p-values on its own. Because what it's done is it said, look, we've done a lot of t-tests, 5% of them are going to be wrong because that's how hypothesis testing works. So I'm just going to bump the p-values up a bit so it's harder to reject. So that's how it does it. Cool, and it will give you a table that compares everyone to everyone with a p-value of its own. And officially that's what it is. So if you've got 3 groups, that gives you 3 comparisons, but if you've got 4 groups, that gives you 6 comparisons. If you've got 5 groups, that gives you 10 comparisons, and 6 groups would give you 15, I think. Yeah, they go up by more each time. Yeah. And so you can see how bad it is if you have too many groups. What else goes in ANOVA? Assumptions. That's the other thing that goes with tests, isn't there? Okay. So, assumptions. All hypothesis tests have assumptions, and the reason they have assumptions is that you're calculating probabilities. You right? Yep. Nah, I reckon in the exam they'll just give you the table of the p-values. Could be wrong. Can't be sure. I'm not the person who wrote the exam. I don't know what kind of psychopath you have. Seems like a nice person, but you know, some people turn into horrible people when they write exams. So this formula here is how it's figured out, but what that means is that there's a mean square E, which is in the table here, and you do a calculation to figure out what the this is a t statistic. They didn't say that, but they've referenced a t here. So this is a t statistic, and this p-value came about from that t statistic. Yeah. So, yep. So I don't think you'll have to use this. Yeah, but this table, interestingly, did not tell you what the t-statistic was, but you could technically calculate it. This mean that they refer to is the difference between these two means, and you could divide it by the square root of MSE. You'd need to know how big the individual groups were. So it's very similar to how the t-test works, where you've got like a 1 over n1 and a 1 over n2. That's in the t-test formula. But my instinct is that they won't expect you to remember that or even use it. I'm very sorry if they do, but I don't think that this is something that's in their, on their mind for this course. In the past, the exam has been very much more, we did an ANOVA, here's the results, interpret them. Yeah. And they're much more interested in getting you to do probability calculations with distributions and whatever, or at least tell you how they would have done them because you don't have MATLAB. Or they'll say, here are 3 MATLAB codes that give results, and then they'll ask you to do a thing and you'll just have to pick the right one. That's how they normally do it. Check out your practice exam for the vibes. Like, you got to go there and see like, oh, cool, they asked me to do a probability and I don't have MATLAB, but they did tell me some code and what it produced. And then, yeah, have a look at that because that's going to be a good picture of the way that they go about structuring their stats questions. So, yeah. There is one last thing. You know how I said back here, everything has a test statistic, right? And you have to compare it to all the test statistics that could have been. That means you're working with probabilities. And all probabilities require you to assume a distribution somewhere. Like even when you roll a die, you assume that it's fair to get a 1/6 for every face. So we're essentially rolling a lot of dice here to calculate our means, and you need to make assumptions in order for that p-value to be an accurate representation of the probability. In order for this F statistic to actually come from an F distribution, you need to make assumptions about the original data and where it came from. And those assumptions are usually that it's normally distributed, the original data. And also that the groups are independent of each other and the people within each group are independent of each other, and also that the final one, which is different from all of the other ones, that the variance in each group individually is the same. So these are the assumptions. Normal distribution for the outcome. And you could assess that with a histogram or a QQ plot. They do QQ plots in this course, yeah? And you would normally do that for each group separately. And you would want independent. And you can't assess independence with a graph. You can only get it from the story. In this notes it says experimental design. What that means is that if they randomly assigned people to the groups, or they randomly chose people from the population, or mainly if they mention the word randomness, then that'll do. Story mentions random choice. That'll usually do the trick. But you can also say, oh, cool, these things were done on different days, it's probably independent. Because it was a factory thing, it's a quality control situation rather than inflicting chili on my friends. Then you could have the 3 different machines, right, and they're all producing different objects, and those objects are independent because they were produced by different machines. And so it's always the story, but you normally mention some sort of random choice. And so independence can only come from the story. And so if they ask you to assess independence and they haven't mentioned randomness, you have to say there is not enough information to tell if they're independent. So an appropriate answer is I cannot tell. Yeah. And then the other one is equal variance. Have they said the phrase homoscedasticity to you? Like the single word? That's what homoscedasticity is the very fancy terminology for equal variance. Homo meaning equal, and scedasticity meaning, apparently, variance. Actually, homo doesn't mean equal, it means similar. No, it could mean who cares? So, yeah. And the way to tell equal variance, technically, it should be a hypothesis test, right? Because you're asking the question, are the variances equal, which is a yes or no question about your data. And so you should be able to do a p-value to answer the question of whether the variances are equal, but you don't. You just do a shortcut. And the shortcut is that you take the biggest standard deviation and divide it by the smallest standard deviation, and if that number is less than 2, then you would conclude that the variances are equal. Is it the variance? Just a second. Oh, yep. The biggest standard deviation divided by the smallest standard deviation, you need it to be less than 2. That there is a test statistic. It's something you calculate from the data, and you compare it to a cutoff value. Technically what you're doing there is a hypothesis test, which I think is really cute. But it's hidden. I didn't say it was a hypothesis test because it's like it's a hypothesis test within another hypothesis test. And it's just, but I think it's funny. I did not know that was a hypothesis test until I had to lecture a course like this. It was years after I learned ANOVA that I realised that that was a hypothesis test. So, yeah, anyway. Fun times. Yeah. So, the classic ANOVA question in an exam will give you all the output, including various graphs. And it will say, assess the assumptions of ANOVA. And you'll say, yep, all those QQ plots are approximately straight. And the biggest variance is less than 2 of the smallest variance. Story mentions random allocation, so it's independent. Yes. Or if any one of them are no, you say no, and then part 2 will say, regardless of what the results of your assessment of the assumptions is, continue to do the ANOVA. And you'll look at the results. And then you'll say, yes, there is a significant relationship between whatever the categorical variable is called and the outcome. And then they'll show you the multiple comparisons and you'll say, yep, all the groups are the same except this one. Something like that. But you won't say it that way. You'll say, there is no evidence of a difference between any of the groups except this one. Normally, instead of saying things are the same, you say there's no evidence of a difference. Because it's statistics, you're never supposed to be hard and fast. It's always supposed to be whether there's enough evidence to believe it or not. How are you feeling about ANOVA? I have one last comment. Yes?
On a couple of pages earlier, you drew a distribution and you showed the area of the.
Yep.
What distribution is that?
That is the F distribution with this many and this many degrees of freedom.
So is it a property of the F distribution that it only has a tail to the right?
I'm going to answer that hopefully correctly. It is a property of the F distribution that it starts at 0 and goes that way. But it's also a property of the calculation that all of the numbers were squared along the way, and so you can't get negative answers. And so you only colour in the right-hand tail. Yeah.
And the p-value is the area of all values further away from the mean than that.
Yep, I'm going to repeat that. P-value is the area of all the values further away than this. Yep.
Why aren't there any on the left side?
Because, bear with me. Because as the means get further apart from each other, the F will always get bigger. Because all the distances are squared. So the minimum that F could possibly be is 0. And 0 is what it would be if all the means were equal. So if all the means were equal, the F statistic would be 0. And if every time you make the means further apart, it just makes the F statistic bigger. And so the top end corresponds to being not the null hypothesis, and 0 corresponds to the null hypothesis. And because it's not possible to be negative, because everything got squared, you only go that side. Does that answer the question? Yeah. Yeah. Similar for the chi-square test as well. If it ever happens in the future that someone does a hypothesis test with an F statistic in it that isn't ANOVA, there are some situations you can set up where it's possible to get the bottom end as well as the top end. But in ANOVA, you can't. The bottom end, the 0 end, is the null hypothesis, and everything above that is not the null hypothesis. And so you can only get the right-hand tail. But just want to warn you, if you ever do any more statistics or see something with an F statistic, it is technically possible to do both sides in some other situations. Just want to be clear on that. I don't want to give you a rule that expires. Okay. I want to make one last comment, and I'm not going to look at the details of how the computer spits things out, but I just want to say what the difference between ordinary ANOVA and two-way ANOVA is. It's called two-way ANOVA because there are two ways to affect the outcome. Two-way ANOVA will be when there are two categories affecting the outcome. So the classic is treatment and dosage. So you have acid wash A and acid wash B, and this one's at concentration 2 molar and this one's at 1 molar, but this one's also 1 molar and 2 molar, and so you can separate things into 4 different situations depending on how the categories combine. So you have A, B, and 1 and 2, and you have A and 1 and A and 2 and B and 1 and B and 2. And in the story, there's 4 groups, but it's really just 2 different categories that are telling you which group you're in. That's two-way ANOVA. And the way two-way ANOVA will be reported is that there will be a row for this category and a row for this category and a row for the interaction. So I'm going to add one thing to this diagram. It may be that one category affects the way that the other category affects the outcome. Like that. Or like this, it doesn't really matter. But that's what an interaction is. So it may be that the dose, like the concentration, makes a difference to the way that the acid makes a difference to the outcome. Or if this was a psychology experiment, it could be that the years of experience of the psychologist makes a difference to the way that the treatment makes a difference to the outcome. But it could be that it doesn't matter. It could be that this makes that no matter which of these categories you're in, switching from here to here always makes the same difference. And no matter which this category is in, switching from here to here always makes the same difference. And that would mean that this arrow isn't there. And so this is called an interaction. So when you look at an interaction, like the table will be, and it'll have like the letter category and the number category. It'll be the name of the category, so it'll be like letter, number, interaction, total. And it'll still have an ANOVA table, and there'll still have SS's, and there'll still be degrees of freedom, and there'll still be MS's, there'll still be MS's, and there'll still be some F statistics. I don't know how they're calculated, though. I couldn't tell you that. I've never paid attention. And I don't think you should either. Just give me a second. Wow. Yep, all of them are divided by the... Oh, no, there's an error as well, sorry. Sorry about that. They'll all be there. And then each of these is divided by the error one. And so it'll be like SS for one of them over the SSE. It'll be SS over the SSE. This will be the SS for that column over the SSE. Yep. And then, yeah, but again, I've never paid attention because no one's ever come back and said, David, you didn't tell me. So, yeah, sorry, MS, for the sake of all that is holy. These will all be divided by their matching degrees of freedom, and this will be MS over MSE. These are the F statistics. Okay, all the F statistics are the matching MS divided by the MS for the error. All right, and the degrees of freedom are the same. It's still the number of groups minus one. So it'll be groups minus one, but this one will have possibly a different number of groups. Maybe there's 3 letters and only 2 numbers. And then the interaction, that'll have its own thing. It'll probably be those 2 things multiplied by each other. Yep. So this will be like the number of groups minus 1, this will be number of groups minus 1, and this will be those 2 things times together. And then the error will be everything else. But I could be wrong about that too. No, can't be bothered. And this is still n minus 1. Okay. Oh, I've put them in the wrong column. Damn. I'll just switch these. There we go. They are going to have to be switched later, but that's fine. Anyway, I don't think anyone will care about that table. I've never seen a question asking you to fill that table in. But all I want to say is the way to read it is that each one will have a p-value to go with it. And so you'll go, and the most classic question is say, is there an interaction between the number category and the letter category? And you come here and go, that p-value is 0.17, and you say, no, there's no interaction. Which means that the number category affects the outcome the same way regardless of what the letter category is, on average. No evidence to suggest that the number category has a different result depending on the letter category. So something like that. That's two-way ANOVA. You can have any number of categories in these places here. It could be 3 or 2 or whatever. But the importance of the two-way is that there are two ways to affect the outcome. And it's technically possible to do a three-way ANOVA as well, but whatever. And it'll just have an extra couple of rows in the table. And they'll be like, yeah, anyway, don't get me started. That's not worth it. I just wanted to point that out because it's something that people have. And that's why the original one's called one-way ANOVA, because there's one way to affect the outcome. All right, let's look at that Taylor series stuff. I hope that's useful. If you want to see what I say about all the other statistical procedures, then there are other videos about it that you can always come and ask me too. I'm just going to go to the toilet, and I'll be back in just a few minutes. I'm not going to pause the recording because I'll forget to put it back on.
semester I got 6 out of 30. It wasn't on the test.
I already got told the exam I passed. He was even in the first day assessment, but it was fine.
I got 6 in this time.
So you guys are so much.
I was so dead on.
All right. Okay. You okay? Okay. Well, I'm back. Thanks for if you're watching this video later, for waiting. You guys had stuff to do. Well, all right. I have to say, you're not the only one. It took me quite some time to figure out what the hell was going on with Taylor's theorem in this course. I still have to make a couple of moves on paper to make myself feel comfortable with it every single time. Yeah. But I do know Taylor's theorem. You know, I do Maths 1B 3 times a year. And so I know the theorem. And so I always start there. And the theorem goes that any function can be figured out from the value the value of it and all its derivatives at one point. And so it will be f of a specific number. I'm going to use c, if that's okay, just for my own purposes. There's a center number, and f of c plus f dashed of c times x minus c plus f double dashed of c on 2x minus c squared plus f triple dashed of c on 3 factorial x minus c cubed, and so on until you feel like stopping. And then the symbol for counting how many dashes there are is a number in brackets. So you don't just put a number there because that means something else. Number in brackets counts how many dashes there are, and it'll be n factorial. So you'll keep doing this, and officially f of x is only equal to this if you go forever. Unless your function was a polynomial, and then you could stop and it would work. And then all the rest of the stuff that will add up, like all the rest of the infinitely many that will add up to what f of x actually is, will be encapsulated in the error term. And so this is now not just Taylor's, this is now Taylor's theorem. Taylor's theorem says that if you attempt to do this and you stop, then there is a way to estimate what the difference is between this and the function that you're interested in. And so there will be an error term here, and it will look exactly like the next term that you would have done. Except instead of C in this spot, you will put some other thing. That's the idea. And in this course, they traditionally put a T in that spot. Back in Maths 1B, they put the Greek letter xi. And some people online use the English letter Z. You can put whatever you want in that spot, but in this course, they traditionally put a T there. For some T between x and c. That is Taylor's theorem. In most things in this course, you will not go past 3, but you never know. Okay. Cool. In this course, because it's numerical methods, in general, you don't in fact have a formula for what f is. All you have are some of its values at some places. Okay, just working on that. Okay, but this is Taylor's theorem, and in my head, the picture is this. Here is C, and if I want to know the value at x, and I know the value here, I know what f of c is and what f dashed of c is and so on. I know as many of the derivatives as I want. And if I want to know what f of x is, then I need to know this x minus c in order to do it. So x minus c is in fact the journey from c to x. That's useful to know. Because if x was on this side, then x minus c would be a negative number, and it would go that way. Yeah. I don't know if that's helpful, but it helps me. So subtraction has always been the journey from one place to another. So, yeah. And so the way that you calculate what the value of f of x is from all of the values at c and the distance between x and c. That's how you calculate it, and that's what this Taylor's theorem says. And there is a number somewhere in this zone that you can sub into this spot that will produce the correct answer. But it may be that the t might be more than c, it might be less than c, depending on whether x is more or less than c. Okay, that's the beginning of it, and I can think all of those things and I can write this down. And I will write it down as far as I need it to, and I may adjust how far I need it to in context. So in this course, in general, the places that you are doing this at are labelled x1, x2, x3, xj, xj plus 1, that sort of thing. So in general, what we actually have is something like this. This is xj, and this is xj plus 1, and we have xj minus 1, and that sort of thing. And the distance between them is h, like that. This is in general how things are set up in this course. Does that seem familiar? And it is, and what we have is not a formula for what f of x is, because if we had that, we wouldn't need to approximate things. What we have is the answer for what f of x is at these places, and sometimes what f dashed of x is at one of those places, and sometimes what f double dashed is at some of those places. That's the information we have. Okay. So in general, you will replace your c with whichever one of these you're interested in, and usually it will be xj. That will be the center that you're going to use. So I'm going to just write the exact thing that I wrote before, but bear with me. Oh, before I finish this, no, I'll just write it again. It doesn't matter. So, I'm just copying what I had on the previous page, because I'm going to change it now. Ready? I want my center to be xj. And so I'll replace all the c's with xj. And that's one of the reasons why I use c, because it's easy for me to turn it into an x. Wait, I did something wrong. This one is not a c, that's still a t. The last one is not the centre. Yep?
If the question says use Taylor series to 3 terms or something, does the error term count as one of those terms?
No.
No.
So if they say Taylor series of 3 terms, the error term is the next one after the 3.
Yeah, so do 3 and then error
Yep.
term with the 4.
Yep. Yes. I'm just going to... We had a question. No. The error would be the 4th term. Technically the 5th term because that's the 0th term.
Oh, okay. Yeah.
Yeah. It's never clear. But if they say go to 3, I would make that to the power of x cubed.
Yeah.
Yeah. Okay. What this means is, now, this is Taylor with centre xj. They won't always say the word centre. They'll say Taylor around xj or about xj or at xj. There will be a phrase that will make it sound like xj is a location. So around, at, about, yeah, or centered at. All of those are things that could be said to indicate that this is where the center is. Okay, so now we're here, and I'm supposed to use this fact somehow to calculate the things I need to calculate. And the center is chosen, and then what changes next is what the x's are. So first you choose the center, and that changes the c to whatever the center is, and then you choose the x and you sub in different ones of these. So you may put in now xj plus 1 and put j plus 1 where all of these x's are. Or maybe it'll be j plus 2 and you put j plus 2 where all of these x's are. So at this point there will be now several of them usually. So this is the setup formula for center xj, but then you will put in f of xj plus 1 equals, and f of xj plus 2 equals, and f of xj minus 1 equals, stuff like that. And you'll sub in for all of the x's that now don't have j's on them yet, and you'll put j's on them. That is normally how you do it. Is this sounding familiar? Okay. Is it feeling slightly clearer? Good, because that's my job. Okay. And the last thing that you need to do is write everything in terms of h. So in your formula, and this is one of the things they don't seem to show very clearly, if you have in your formula xj plus 1 minus xj, that's the journey from xj plus 1 to xj. Sorry, from xj to xj plus 1. So when I think about this, here's xj, and here's xj plus 1. When you subtract things, it's from the minus thing to the plus thing. That is that journey. That's what this is. And that distance is h. But if I had xj minus 1 minus xj, that's the journey from xj to xj minus 1, and that is minus h. Whereas xj plus 2 minus xj, that's the journey from xj to xj plus 2, and that's 2h. And that means that when you see in your formula this thing, you replace them all with 2h. And then you get 2h in brackets squared and 2h in brackets cubed. And that's going to cause the 2 to be squared or cubed. So that's the next step. Anything more than that, I have to do a proper example to make it make sense. But that's the general vibe of how to get from Taylor's theories to the thing that you want. So I write down Taylor's series, I replace C with whatever xj is, and then I do each one separately until I've got an expression that uses f x and the various values. Okay. Pretty sure. Right. That's Taylor's theorem. Okay. Right. Yep.
Well, then you assume, then we assume that you'll be given a value t that you have all the derivatives to y and the value u.
No. No one ever knows what t is.
Okay.
Oh, useful to point out though that when you sub in xj plus 1, it will have its own t that will be different to the t that where you sub this in. This will be like t minus 1 and this will be like t2. Every value that you sub in will have its own different t. That's really important. I mean, actually, it's not important. I've just got that's okay. A notification for something that's happening in the other seminar that's going on at the same time. So technically it's because I made the meeting. It's okay. It's fine. So yeah, each one has its own value of t. To be fair, it doesn't really matter. The calculation will work out the same anyway. But someone will get upset if you don't do it that way. Because technically, every t is different depending on what the x that's subbed in. Yeah. Okay. So I should really do an example, and I do not want to make one up. So I'm going to get one. Okay. Okay. Where's the rest of my paper? So I'm going to take one of them from the notes that didn't have a proof in the notes. Not that any of them have a proof in the notes, that's all in the videos. Okay, so we have values of f of x at equispaced points equispaced points xj with grid spacing h. That's the classic setup, and that's a description of the drawing I made earlier. And show that the finite difference formula f dashed xj plus 1 is approximately 3fj plus 1 minus 4fj plus fj minus 1 over 2h has error of big O of something. I'm just going to pop something in this spot later because I don't know what it is. Usually in an exam they'll tell you what that is. It'll be squared or cubed or something. But I don't know what it is yet because it's not in these notes, so I'm going to figure it out as I go. They could ask, find the order of the error. And you could have to do it yourself. But most exam questions, in my experience, what people have told me, tell you what order it is. And in general, if they tell you an order, you want to go a little further than that in your Taylor series. So here's my thing. we're going to divide by 2h. So if this was like a 2, for example, then the top would have to have an h cubed. So you'd need to go to the to have the an h cubed in the error. That's the idea. So if this had an h squared, then I'd need to go a little further, so that when I divide by h squared, it comes out to be an h whatever. Okay, here we go. That's the question. And my answer is this, and I'm going to draw my picture first, and I know it seems silly, but it's not silly to me. Here's xj, and here's xj plus 1, and here's xj minus 1. Okay? And they are all of the ones that are mentioned in the story. J minus 1, j, and j plus 1. So I'm just going to draw them all in my picture. And the distance between them is h. And what I'm doing is I'm figuring out what is happening at this point here, f of xj, f dashed of xj plus 1. No idea at the moment, but I'm just thinking about it. This is where I want f dashed here. That's what I want a formula for it. So it seems to me that I should use xj plus 1 as my centre. Because in Taylor's theorem, the only place where you mention the derivative is at the centre. If you go back to your Taylor's theorem, in fact I'm just going to write it here, f of x and I'll stop at some point. The only place where there's derivatives mentioned is at the centre. So I'm never going to make a formula for f dashed of xj plus 1 unless I put xj plus 1 in that spot. That's my first piece of reasoning. I'm pretty sure it's good reasoning. So I'm going to put xj plus 1 as my centre, because that's the place I need where the derivative is. Because at the moment, all I have is the function values. I don't know what the derivative is there. So, yeah. So here we go, xj plus 1. And there'll be other stuff. We'll deal with that in a minute. I don't know how far to go yet, but I'll know soon enough. And so, since I have mentioned f, where'd the problem go? Since I have mentioned fj and fj minus 1, then I will use Taylor's theorem at those places, at j and j minus 1. And I'll just leave a bit of room and fix that later. I don't know how far to go yet. Cool. And then I can put my h's in for this one. And I'm also going to replace this with fj plus 1, because that's what it is. Just to make my life a little easier. And this is fj. Yeah. Now, this is the journey from j plus 1 to j, which is this way, and so that is minus h. Don't know if I have to go any further. I'll fix that later. And so this is where I am. I'm doing okay. All right. And fxj minus 1 will be fxj plus 1, which is still there, plus f dashed xj plus 1, xj minus 1 minus xj plus 1. plus f double dash xj plus 1 on 2 xj minus 1 minus xj plus 1 squared, and then extra stuff. And so I've got that fj minus 1 is fj plus 1 plus f dashed xj plus 1, and this is minus 2h, because I'm going from j plus 1 all the way down to j plus 1. J plus 1 down to j minus 1. That's 2 h's. Okay. Sure. So I need to compare this to my original thing that I've been told to create. I'm going to need to make 3 of the j plus 1s. That's okay, that's just going to be exactly the way it is, because I don't need a Taylor series for fj plus 1 because I know what that is. And I'm going to need minus 4 of the j's and 1 of the j minus 1s. So I'm going to make those things. Okay. So I've got 3 of the fj plus 1s, and that's just going to be 3 of the fj plus 1s. Because that is the centre, I don't need a Taylor series there. And I'm going to have minus 4 of the fj's, and that's going to be minus 4 of this thing. So minus 4 fj plus 1s. And the minus 4 is going to cancel out that h, so I'm going to get plus 4 f dash of xj plus 1 h. And then minus 4 of this, but that squared is going to cancel out the minus, so I'm going to get, but I'm going to divide by 2. So timesing this, I'm going to get minus 2. J plus 1 h squared. And there'll be other stuff going on there which I'll fill in later if I need it. Okay? Sweet. So when I times this one by minus 4, that squared cancelled out the minus. So I did 2 things at once, which is a bad move, but that's what I did. And then I also need 1 lot of fj minus 1, and I know I've already got it written down, but I just want to rewrite it on this page so they're all together. I always forget to turn off my notifications for Teams. Oh crap, I've just written, what am I looking at? I'm trying to look at the wrong line. I'm just going to look at this line so that I don't get distracted. So it's not a 4h, it's a 2h there. Minus 2h, and this will be a plus 4h squared divided by 2, so 2h squared. Okay. Done that right? Right. Okay. So these are the 3 things that my formula says I'm supposed to combine on the top line there. And when I do add them together, lo and behold, that's 0. Excellent. That's great. And when I add together the ones with the f dashes, I've got, maybe move the h there. When I add together these ones, I get 2h, lots of f dashed. Oh, that's cool, because I have to divide by 2h. Ah, convenient. And then when I add these 2 together, they cancel out. Ooh, so I definitely need the next one. Because these 2 cancelled out, so I'm going to need 1 more. If these didn't cancel out, I would replace these with a t. But I need 1 more after this place where they cancel out. I should probably just do a quick mind thinking here and say, well, when it was like, I should probably do the calculation to just see if the next one cancels out as well, but I can't be bothered. I don't know. I should, just a second. So if I went to the cube, I'd be dividing by 6. Damn it. I have to go to the cube anyway. So let's go to the cube. So I'm just going to go back. No, I'm not going to go back. I'm just going to do it here. No. I hate doing it when I don't know what the level to go is. Freaks me out, but that's okay. I can come back here and I can put it in here. So this one will have an f triple dashed xj plus 1 on 6 minus h cubed. This one will have an f triple dashed xj plus 1 on 6, and this, oh, not there, triple dashed xj plus 1 on 6, and this will be minus 2h square cubed. Okay, and then when I multiply this one by minus 4, so that minus h cubed will give me a minus h cubed, the minus can come out, and then I times by 4, I'll get 4 6, so there'll be a 2/3 there. I'll times by minus 4. And this one will have an h cubed in it. And then this one will have just exactly what it is, because it's just plus, isn't it? Yep. So this one will have 1 6, only it'll be 2 cubed minus 2 cubed, so minus 8 6. What's 8 sixths? 4/3. H cubed f triple dashed xj plus 1. Right, and they do not cancel. This one's plus 2/3, this one's minus 4/3, I end up with a minus 2/3 overall. Because they don't cancel, that's where I'm stopping. And so I will go back one more time and change this to a t. Which is why I don't write it in pen. Okay. Right. And I've chosen different letters for t. I've done t0 for j and t minus 1 for minus 1 just to match up with how far from the j's they are. And then now when I add these all together, the total is now, these cancel. This comes out to 2h lots of f dashed of xj plus 1. And these come out to whatever the crap they come out to, right? But it is definitely h cubed times stuff. They've both got an h cubed, which is the important bit. And so therefore the total on 2h will come out to f dashed of xj plus 1 plus half of h squared, because we divided by 2h, times constant. And it's okay to write the word constant at that point, because this is a constant. T0 isn't a variable, it's an unknown. It is a specific value of x that we happen not to know. And so this is big O of h squared, because it is a constant times h squared. Yep?
Can you then integrate the half into the constant, or do you just make...
Yes, you can integrate the half into the constant if you like. But like technically this is a new constant. Yeah. But I just wanted to put it there to make myself believe that I had done something. Yeah. And so therefore the error is big O of h squared, because that's the error there. Yeah. So if they had told me it was big O of h squared, I would know right in advance that I would stop with my t's in the h cubed position, because I was dividing by 2h here. So if they had told me it's big O of h squared, then I would have known in advance that I should have stopped here and put the t's in at the third derivative. Yep.
So if you had h squared on the bottom, would you then go to...
If I had h squared on the bottom, I'd go to the fourth one. So that h to the 4 divided by h squared is h squared. Yeah. Yeah, so you want to make the numerator as many more compared to the denominator depending on what the big O is. Yeah. And my favourite part of doing it this way, of literally writing each part of this down as a separate line, is that once you've done it, you actually start to see that things will cancel and you feel like you've done something right. And it gives you some hope that everything's going to work out okay. But if I try and do it all in one big calculation sideways, I can't see that I'm getting anywhere. Whereas if I write it this way in 3 separate things, then I can see it. And especially lining up the derivatives. I mean, even this, I would still want to put my page sideways so everything lined up better, but it's okay. So don't be shy in using all of that. You know how that traditionally in exams every second page is blank? Don't be shy to use as much space as you need, because if that's what you need to get it right, then you'll get it right. And whoever has to read it, it's their fault for not giving you enough space. So don't stress out about them not seeing you're working. That if they give you questions like this, they deserve what they get. Okay? You need to do what you need to do. Ignore the amount of space you've been given and use all the space you can. So that's just my advice. You've seen me. I cannot fit anything on the space that they would give me in the exam. But that's okay. Just become zen about it. Yes, anyone who's ever been diagnosed with a learning difficulty knows that you just do what you need to do. And everyone else can learn that same lesson. Okay, right. And there we are at past. And I think that's time to stop. Unless there's any other questions about what I just said there. You'll get an email with these notes and the video and stuff. So, yeah.